In this video, we're going to be talking about limits to infinity, where the notation for the limit looks like this. So you measure the behavior of some function as x approaches infinity or negative infinity. And you're measuring the behavior of the function. Keep in mind, not what the function equals to at the end. So let's give you an example of a function 1 over x. So the standard function 1 over x, the first example you get of a function that has an asymptote, looks like this. Now if I drew it better, maybe it would look, there you go, that looks better. Looks like this. And it has a vertical asymptote where this red line goes and shoots up to infinity, and this shoots down to negative infinity. But it also has a property called a horizontal asymptote. So first thing you learn about asymptotes is vertical asymptotes. They're pretty easy to find when the denominator hits 0, but horizontal asymptotes are less obvious. So a horizontal asymptote goes all the way and keeps going, but it never approaches 0. So however large of a number you put onto here, let's say you put, so let's try to draw this onto infinity as an example. So the function of this is 1 over x. Let's say you put a 1 over 1,000. Well, that's still not 0. What if you put 1 over a trillion? Okay, a trillion is 10 to the power of 12. 1 over 10 to the power of 12. Well, this limit, or this function, sorry, does not approach 0 at all. It's just 1 over 112. Although this is still a very small number, super close to 0, it is not equal to 0. So no matter how large of a number you put in here, 1 over a quintillion, a decillion, a googolplex, you're never going to get to 0 unless the denominator is equal to infinity. So unless you get 1 over infinity, you cannot approach 0. So the behavior of this function as it approaches infinity reaches 0 in a sense, but it actually never reaches 0 technically. Now, how do you solve for these limits to infinity? Well, you understand what a horizontal asymptote is now. It just keeps getting smaller and smaller, but it never touches 0. So the number will get to like 0.000000001, but it will never reach 0. Okay, the function value will never reach 0. So that is the concept of a horizontal asymptote, and you can use limits to infinity in order to solve for this. So I'll show you a very trick. It's kind of a trick technique. It's a little bit of cheating, but it's a technique that works for solving limits to infinity. So for the problems I'm going to give you, I'm going to try to cover all the bases for limits to infinity, including the ones that don't have horizontal asymptotes. But I'll give you a hint. This problem has a horizontal asymptote right now. And how can I tell? Well, I'll show you by solving the problem. So let's solve this problem. And what we're actually going to do here is a little bit of a cheat, but we're going to take the exponents in the numerator and denominator and ignore all the lower level exponents. So if you look at the exponents, this is technically x to the power of 1. This is 2 times x to the power of 1. These are the highest order exponents. So the exponents that are powered by the largest number. And currently x to the power of 1 and x to the power of 1 are the largest exponents. These 5 and 3 values, they don't have any exponent values, so we can just completely toss them out the window. So when you're solving for limits to infinity, only care about the large exponents. And the reason why you only care about the large exponents is because they contribute the most to the problem. Once you're approaching infinity, the difference between x to the power of 2 and x to the power of 3 is absurd. So when you're approaching infinity, it doesn't matter. Like if you had let's say you had a function x to the power of 3 plus 2x to the power of 2 and 3x to the power of 3 plus x, right? These parts of the problem as the limit approaches infinity don't even matter. The x to the power of 2 has nothing compared to the cube, so it literally does nothing. Okay? Like these x squared and this x to the power of 1, they're useless, basically. They don't contribute anything to near infinity. That's why we can just completely ignore them when we solve for horizontal asymptotes. So now that we just removed everything but the largest exponent values inside of our function, we get left off with x over 2 to the power of x. And we're actually going to do this problem. I just wrote it out right now, but I think this is a good problem to do. So the limit as x approaches infinity for x over 2x, well, what can we do? We can factor out x. So when we factor out x, we just get 1/2. But there's no value of x here, correct? So since there's no value of x, well, we can remove the limit symbol. That means our answer is just 1/2. So that's why you only care about the largest exponents. Well, usually, if the value of the exponents are the same, you're going to get a horizontal asymptote by just canceling out the exponents. So for this problem, you have the limit as x approaches infinity for this function here. Well, what did I say? We ignore every single exponent, every single term, right, other than the largest exponent terms. So we click Control X. We disinclude these, and all we get left off with is x to the power 3 and 3x to the power 3. So we can actually factor these out, and you get 1/3. And our horizontal asymptote, or our limit to infinity, well, is just 1/3. And in the cases for horizontal asymptotes, even if this approached negative infinity, it would still be the same. You would still factor out the you would still just cancel out the smaller exponents, even if it was for negative infinity. So this problem looks slightly intimidating, but trust me, not that bad. Remember what I said literally just now. Well, to you guys it was literally just now, but I paused the video to write this. But to you guys it was just now. The limit as x approaches negative infinity applies the same rule. So you only care about the largest or the highest order exponent. So let's disinclude everything from the numerator. So the numerator is the largest exponent, x to the power 4. Disinclude this, disinclude this, disinclude this. All right, what about the denominator? Well, the denominator is large exponents, x to the power 4 as well. So when we rewrite the limit, we get sort of just negative 10x to the power 4 over 2x to the power 4. Well, again, we can cancel out x to the power 4, and we get left off with negative 10 over 2. Therefore, our horizontal asymptote in this case, or limit to infinity, is -5. Now, sometimes in a test, you might see, oh, find the horizontal asymptote. Well, you can do this same exact thing. In pre-calculus, you probably learned how to find the horizontal asymptote using this highest order exponent method as well. So you can just do the same thing. If you see a limit to infinity, just cancel out all the smaller exponents and then leave the largest ones. Well, how about a little more complicated limit to infinity? You have a square in the denominator, but you have a normal function in the numerator. What do you do here? How can you cancel things out? Well, same rules apply. You can just cancel out the ones that are the lowest power order of exponent. So you can cancel out this and cancel out this. As a matter of fact, if you cancel out negative 9x, you could simply just erase that part of the square root. So when you're solving this limit to infinity, you can do 7x divided by the square root of x squared. So I just completely removed the minus 9x and the plus 4 from the numerator. So what is this also equal to? Well, this also equals to the limit as x approaches infinity for 7x over x. All right? Because the square root of x squared is just x. So 7x over x is just cancel out the terms for the x, and then you just get left off with 7. There you go. The limit to infinity for this is 7. So when you see, in the case of seeing a square root, you can still do the same thing. You just cross off everything inside of the square root that isn't the highest order exponent. Now, how about in the case where the denominator's exponent is greater than the numerator's exponent? So sometimes you're not going to get a larger exponent at the top. So maybe you get 3x to the power of 2, but you get x to the power of 4 in the denominator. Sometimes that's going to happen. So how do you solve for a limit to infinity with this? Well, same thing applies. If you just, you can kind of, this is not necessarily right. You can't plug in infinity, but you can just replace x with infinity. Well, infinity squared, right? 1 over infinity squared is just 1 over infinity, right? Infinity squared is just still infinity. There's no number past it, right? So 1 over infinity is just 0. So this limit to infinity is 0. So when the denominator has a greater exponential value than the numerator, so the bottom part of the fraction has a greater exponential value than the top part of the fraction, then your limit is equal to 0. So maybe another less obvious example of this is 3x squared plus 3x over x to the power of 5 minus 9x squared. All right. So we just cancel out all the non-highest order power exponents, and you just write down 3x squared over x to the power of 5. But when you simplify this, you get left off with, well, you simplify just the function, you get left off with the limit as x approaches infinity for 3 over x to the power of 3. So I factored out the x squared values from the numerator into denominators. And then what actually happens is, well, if you plug in infinity in the denominator, you get 3 over infinity, which is just 0. So if the denominator has a greater exponential value than the numerator, the limit to infinity is equal to 0. Now, we talked about if the denominator was greater than the numerator's exponential value, but how about if the numerator's exponential value is greater than the denominator's? Well, let's rewrite this limit. As always, limit to infinity. You just cancel out the non-highest exponents. So you get left off with 3 times x to the power of 5 over x to the power of 2. Well, we can factor out x to the power of 2 here. And we get left off with 3 over 2 x to the power of 3. But if we just directly plug infinity here, well, 3 over 2, so 3 over 2 times infinity cubed, which is just still infinity, so infinity cubed is just still infinity. Well, infinity times anything is just equal to infinity. So if your greatest exponent is at the numerator, then you have no h asymptote, or horizontal asymptote. So the function just goes up to infinity. Like in the case of, also familiar function, of a parabola. So x approaches infinity for x squared, your parabola, standard parabola. What happens? Well, if you just plug in infinity, you get infinity squared. So technically, there is no boundary. Your function goes on to infinity. Now, how about in the case of negative infinity for this case? Well, in the case of negative infinity for x squared, you just get negative infinity squared. But anything squared that's negative is just positive, so you just get positive infinity. So your limit as you approach infinity can also equal negative infinity, but that's for when you have like negatives in the front. Like if you have the limit of x approaching negative infinity for, let's say, just the function negative x. Okay, how about that? Just for the function negative x, that looks like this. So negative x is just a straight linear line with a slope of -1. So as x approaches negative infinity for negative x, we get negative x, which you substitute negative infinity into x, you get negative infinity, which is just positive infinity. So as x approaches negative infinity for the function negative x, you get a positive infinity. And that actually makes sense because this function just keeps going and going and going. No matter what number you plug into x, you can just it keeps going up and up and up. So as you go to negative infinity, as x approaches all the way back here, well, this function just kept rising and rising and rising. And if it rises, then it's going in the up direction, which is the positive infinity direction. So this makes sense. And how about if the limit for negative x approaches positive infinity? Well, you just plug in infinity here and you get negative infinity, right? Just plug in infinity into the x and you get negative infinity, which makes sense since as you approach, or as you keep going right, more and more right, you just keep getting lower and lower and lower, all the way down to negative infinity. So, as always, if you have any questions, put it down in the comment section. And if you found this video helpful, consider subscribing. I would greatly appreciate it. Thanks for watching.